Volcanic gases can be telltale signs of what is happening in the subsurface plumbing system. The chemical composition of the gas and its emission rate can be signs of unrest and give us warning signals before an eruption occurs. Once an eruption has started, volcanic gases can inform us whether the eruption is stable, whether it is increasing or changing in character, or coming to a stop. Consider the two figures shown here. Figure A shows the composition of a gas from a fresh, undergassed magma straight from a deep mantle source. Figure B shows the gas composition of the same magma, but after it had been stored at a shallower depth. The most striking difference between A and B is a decrease in the amount of carbon dioxide, which happens during the storage of the magma at shallower depth. The amount of water, sulfur and halogens has also decreased, but not as dramatically as the amount of carbon dioxide. This shows that different gas types behave differently in the magmatic system. Carbon dioxide escapes from the magma much earlier than other gases. Now imagine that you have been monitoring gas emissions from a volcano for some time, and the gas composition has always been like on figure B. But one day you find that the composition has changed from B to A. This could be a sign that the amount of fresh magma has arrived from depth into the shallow system. The scenario which I described previously happened in real life at Kilauea volcano in Hawaii. Kilauea is a volcano which erupts very frequently, and the location of the eruption vent can change, so it is monitored very closely using many different techniques. Gas emissions have been monitored for many years. The carbon dioxide emission rate increased between 2003 and 2004 from 8,000 tons a day to 20,000 tons a day, and it remained high until 2007. This was a result of increased volume of magma arriving from mantle source and accumulating in the shallow storage area. In 2007, there was a dike intrusion towards the surface and an increase in eruptive activity. My collaborators and I recently discovered that Katla volcano in Iceland, a very hazardous volcano which last erupted 100 years ago, is emitting a lot of carbon dioxide. We found that it is one of the top 3 emitters of volcanic carbon dioxide in the world. Gas emission rate from Katla was measured for the first time in 2016 and again in 2017, but is not being measured continuously or regularly. We saw that in those 2 years, the emission rate from Katla was much higher than from any other volcano in Iceland. This graph shows comparison with Grímsvötn volcano, which is a frequently erupting volcano, and Reykjanes, which has a very active geothermal area. Katla dwarfs both those volcanoes in terms of carbon dioxide emissions. In fact, the emission rate of Katla is more similar to the emission rate of Kilauea volcano in Hawaii between 2004 and 2007, when Kilauea was undergoing increased magma accumulation. We don't yet know if the high carbon dioxide emission rate from Katla is a sign of volcanic unrest, or whether this is normal quiet state of this volcano. But these measurements suggest that Katla should be continued to be monitored closely using many different techniques. Sulfur dioxide is an important gas for monitoring active volcanoes. The emission rate of sulfur dioxide is related to the volume of degassing magma. This graph shows the amount of sulfur dioxide emitted by eruptions in the last 10 years, detected by satellite measurements. On average, larger eruptions have also larger sulfur dioxide emissions. Sulfur dioxide measurements can therefore inform us about the size of the eruption and whether the eruption is likely to continue, increase, or stop. As we have seen, gases can be important signs of activity in the plumbing system. But there is also another important reason for measuring volcanic gases. Volcanic gases can have serious and widespread impact on the environment after they are emitted into the atmosphere. As this cartoon shows, volcanic emissions contain gases, aerosol particles, and sometimes ash. If the volcanic emissions get injected into the upper layers of the atmosphere, they can impact climate on hemispheric and even global scale. If the volcanic emissions stay in the lower layers of the atmosphere, where we live and breathe, so to speak, they can impact the environment, property, and human health. Many of the components are toxic or damaging and can have an impact where they get deposited either settling out like dust, which is called dry deposition, or when they are washed out by rain, which is called wet deposition. Following large eruptions, which inject gases high up into the stratosphere, there can be a drop in global temperatures of up to 0.5 degree Celsius. And this drop in temperature lasts 2 or 3 years. This is enough to cause a noticeable change in weather. For example, the year of 1816, following the eruption of Tambora volcano in Indonesia, became known in the UK as the year without a summer. It is said that inclement weather that year even prompted Mary Shelley to create Frankenstein. The graph on the left shows the eruptions since 1880 which have caused a drop in global temperatures. The temperature drop, as I mentioned, lasts 2 or 3 years. The reason is that sulfur dioxide gas, when it gets injected into the stratosphere, gets converted into tiny particles called aerosols. And these small aerosol particles stay lofted in the stratosphere for that amount of time. And while they're up there, they act as a sort of blanket over the planet. They prevent sunlight from reaching the surface, therefore causing cooling. The very large eruption of Pinatubo volcano, which happened in 1991 in the Philippines, was one of the first eruptions where the formation and global dispersion of aerosol particles was measured. The graph on the right shows the Earth before the eruption, 1 month after the eruption, 3 months after the eruption, and finally 2 years after the eruption. The deep blue color before the eruption indicates that there was low amount of aerosol. Within 1 month of the eruption, the aerosol particles have circled the planet, shown by the red belt around the equator. After 3 months, the aerosol has spread over the whole planet, including the poles. And finally, after 2 years after the eruption, the aerosol concentrations are still elevated compared to before the eruption happened. Eruptions which are not as powerfully explosive as the likes of Pinatubo disperse their emissions in the lower layers of the atmosphere, and here they can pose a hazard to people's health, the health of animals, plants, and the rest of the environment. Many volcanic gases can be toxic and deadly in high enough concentrations. Photograph number 1 shows the aftermath of a tragic event at Lake Nyos in Cameroon in 1986. Carbon dioxide gas had accumulated in the waters of a lake inside the volcano's crater, and it got released very suddenly and unexpectedly, and this resulted in a loss of life for many people and animals. Photograph number 2 shows evacuation of tourists from a popular spot at Aso volcano in Japan. This is because sulfur dioxide gas is very dangerous, particularly to people who suffer from asthma. They can start to have respiratory problems even at very low levels. But at high enough levels, sulfur dioxide can be dangerous to everybody. Therefore, sulfur dioxide gas needs to be monitored in places where people are present so that they can take protective measures. On photograph number 3, you can see a metal container disintegrated. This is because volcanic gases and the rain that falls through them tend to be very acidic, with pH as low as 1 or 2. And you can see metal objects get to this kind of disintegrated state just in a matter of days. And most plants can also not tolerate these kind of conditions. Photograph number 5 shows coffee leaves burned by volcanic gases. However, some plants seem to tolerate or even like such conditions. Local farmers on Masaya volcano in Nicaragua have told us that particular plants, pineapple and dragon fruit, seem to like these kind of conditions and grow better. It's still unknown why some plants are more tolerant, more resilient to volcanic emissions, and is an area of research that is very, very important. Final photograph I'd like you to have a look at is of the bad teeth. This is caused by excessive fluoride in drinking water, as can happen near active volcanoes. And the damage to the teeth seen there is called dental fluorosis, when enamel of the teeth gets damaged. This can also be very dangerous to grazing animals when excess fluoride falls out on grass. In the late 18th century in Iceland, there was an eruption called Laki, and it resulted in deaths of 90% of grazing livestock due to damage by fluoride to their teeth and bones. These photographs show only a few selected examples of how volcanic emissions can impact the environment and health. There are many, many more ways that volcanic emissions can have an impact. And as you've seen, the impacts can vary in their type, but also duration and severity. And due to this huge variability in the behavior of volcanic emissions, it's clear that the potential hazards and benefits have to be assessed at each volcano on an individual basis. Each volcano is an individual and has to be understood and monitored as such.